Good day, everybody, and welcome to our second OptiSPICE webinar, this one titled Basic Examples and Analysis. My name is Brian Tipper. I'm the VP of Sales and Marketing here at OptiWave, and we'll be sitting alongside your host, Jem Bonfil. To begin, let's review the webinar layout quickly. So during the presentation, we will hold two question and answer periods. The first one happening about 20 minutes in, and the second one happening at the very end. We'll not be taking any questions via the raised hand option, so please type all questions into the questions section only. I'll also be launching 3 polls such as the one you're looking at now during the course of the presentation. If you're in attendance for all 3 polls, you'll be entered into our $50 gift card draw, and you can find the winner of that draw on our website at 10 a.m. Eastern Standard Time today, so an hour from now. And lastly, we'll be recording the webinar and distributing it to all registrants via email. You'll receive this email with the link to the video tomorrow at 10 a.m. Eastern Standard Time. So basically 24 hours after the session ends. So without further ado, I'd like to hand it over to your presenter, Product Manager of Optoelectronics, Jem Bonfil.
Hey Brian, thank you very much for the introduction. Today I'm going to be talking about OptiSPICE, and initially I'll go over some basic background, and then later I'm going to be introducing some application examples. So let's start talking about SPICE. Our OptiSPICE is based on standard Berkeley SPICE, which is commonly used for electrical analog simulation. What Berkeley SPICE does is it takes equations describing basic components, and then also it takes how these components are related to each other, and it puts them in a system matrix and solves them simultaneously. It can either do transient simulation or operating or AC simulation. Now in our OptiSPICE we extend this concept into optical communications, where we have normally in SPICE you have your electrical variables. They would be voltage or current, and they're all real numbers. In OptiSPICE we have optical variables that are complex numbers. They're either represented as magnitude and phase or real and imaginary. Optical signals, the way we model them are we get the channel, and we actually simulate the envelope of the carrier frequency, and we simulate the phase. So the magnitude of the signal is the magnitude of the carrier, and the phase would be the phase of the carrier. The reason we do it this way is because if we actually want to simulate the full carrier, we would have to go in very small time steps, because the carrier signal usually in optics is in terahertz versus our electrical signal bandwidth is in tens of gigahertz. So in order to save simulation time, we're only modeling the envelope, but since we have the phase, we can still model interference effects and delay. Our OptiSPICE has both linear and nonlinear electrical components. We have well-known resistor, capacitor, inductor as linear components, or for nonlinear we have transistors, BJT, and MOSFET models. So it does what a regular SPICE does. On top of that, like I said earlier, we have optical signals, and these optical signals are represented by they represent a mode, a frequency, and a polarization. And they're all bidirectional. So SPICE can handle all these internally. So we do time domain and frequency domain simulations. We can do wavelength sweeps with lasers. Doing the simulation this way has many advantages, and I'll go over some in the next slide. So one of the strengths of OptiSPICE is actually being able to simulate optoelectronic control circuits. For example, and we can also simulate thermal effects as well. So I'm just going to give you a basic example. Let's say you have a laser, a few lasers, and you have a mux, which is configurable. And the way you configure it is actually changing its temperature. And we have a bunch of ring resonators that does the muxing. If the lasers heat up and we're controlling the resonant frequency of the ring resonator, what might happen is the ring resonator is the resonant frequency of the ring resonator is going to shift. Now we can have alongside this, we can have an electrical circuit that is keeping the ring at resonance by changing its temperature. So all these systems, you can integrate this in OptiSPICE and simulate it all together. Another good application for OptiSPICE is simulating optical links, including the electrical part, where you have a laser driver, for example, if you're doing direct modulation, where your laser driver is an actually electrical circuit with transistors. And then we have nonlinear laser models modeling the behavior of the laser. So then you can generate your optical signal. You can push your signal through an optical fiber, and then on the other side you can have your photodiode and other amplifiers, electrical amplifiers, following the photodiode like a transient impedance amplifier, and this can be all simulated in one environment. As I mentioned in my first example, you can do multi-domain simulations, thermal, optical, and electrical. Thermal, we usually simulate them as an RC circuit. One final point I would like to mention is actually simulating a full photonic integrated chip, including electrical and optical components. We're working towards being able to bring actually models and devices from fabs that manufacture integrated circuits into our circuit simulator, and working alongside third parties that do layout generation for optics, and such that you can actually model your full photonic integrated circuit in OptiSPICE, and then use the layout tool and iterate between the layout tool and OptiSPICE and get your desired design. So now let's go over to some basic applications I am going to talk about today. The first one is direct and external modulation, how you can simply set up this in OptiSPICE using our voltage-controlled laser source. There are a few different ways OptiSPICE and OptiSystem can interact. One of them is actually loading the results from OptiSPICE into OptiSystem. The other one is actually simulating OptiSPICE and OptiSystem components together. So I'm going to talk about that. I'm going to show you a few ring resonator simulations and talk about one of our most basic component called a multi-layer filter and why it's important to know the difference between them. And then finally, I'm going to talk about how we can do a basic mux Dmax circuit using OptiSPICE and why subcircuits are useful. So we have a few different kinds of modulation formats that OptiSPICE is capable of achieving. Modulation types. External modulation, we could just use a basic Mach-Zehnder modulator. Just this waveguide here actually represents a delay, a difference in length between two arms, and this electrical pulse generator, it actually controls the refractive index of the Mach-Zehnder modulator of the one arm, so it can introduce a phase shift and modulate the signal. The other way to do it is actually using our built-in Mach-Zehnder modulator, which, additional to what the ideal one does, it can also take into account the filtering effect of the metal contacts. The final one is an electroabsorption modulator. You can actually, we use for the electroabsorption modulator, we can use rate equation models. So you can use this either as an amplifier or an absorption modulator. And the model keeps track of the change in the carrier density and photon density and modulates the signal. So the other three examples I have here are just basically direct modulation. This is our most commonly used laser. You can control the magnitude from the top arm with a voltage and the phase from the bottom arm, again using another voltage. Here I'm just changing the magnitude. You can also use this laser by controlling the real and imaginary part of the optical signal by changing one variable and one parameter inside the device. Second one is this is actually a subcircuit where I have used the same icon as the direct modulation, but internally it represents a laser with a certain bias that doesn't change very much, and it has a certain RC filter in it that represents how the laser behaves when you modulate it. Finally, we have the laser rate equation model. This actually works with a current that is pushed inside the laser, and again, it uses rate equation model, so it keeps track of the light and the average carrier density inside the device, and models the behavior of the laser. Let's go and actually run this simulation. I have them here all together in one. Now you can see the OT1 is right here, so you can see the result. And here's VC is our input. And then you can actually put these signals all together and see how different modulation types behave, or modulation schemes behave. And so this was the external modulation. Now I'm just going to use the direct modulation, so you can see the RC effects, the filtering effects of the signal on different lasers. Okay, now let's go back to our PowerPoint and continue. OptiSPICE is also able to create different modulation formats. We support AM, FM, and so amplitude modulation, phase modulation, and frequency modulation. You can also do amplitude shift keying, phase shift keying, frequency shift keying. You could do QAM and various different types of modulation formats. And the top one, again, I'm using a direct laser, and this is actually configured as to take in a real number at the top and the imaginary number at the bottom. And here you can see the output. This is actually generated by system. Where I have done this simulation and loaded the results into OptiSystem, and I'm going to briefly show how to do that quickly. So let's go back to our examples. Let's run the simulation first. Now, actually, there are a few details that is important when you're using OptiSystem and OptiSPICE together. One of them is the transient simulation time. It needs to match, OptiSystem and OptiSPICE needs to have the same transient simulation time. And if you're loading results from OptiSPICE into OptiSystem, it is also important to make sure that the sampling rate is set correctly. Even though here it says the noise bandwidth, this noise bandwidth allows, this setting allows you to do noise simulations in SPICE and make sure that you have the correct bandwidth when you're doing the simulation, which restricts the time step to be uniform, because OptiSPICE allows non-uniform time stepping. But when you enable noise simulations, the time step is forced to be uniform, therefore you can set a sampling rate. Now let's run this simulation. Now I'm going to launch, I can actually launch the waveform viewer and look at the results. This is one way. This is the standard SPICE way, but it doesn't give us much information here. Now instead of doing this, I can launch OptiSystem. As you can see now, OptiSystem generated an output from SPICE. This is one of the optical signals. By right-clicking on the port and looking at the port properties, you can see that it's coming from the first laser. One thing I did not mention here, actually, OptiSystem uses the probes of OptiSPICE as an input. So whenever you place a probe, it is an input to OptiSystem. Now, first thing I need to do to look at The results is I need demodulators, receivers. Let's put 2 of them because I want to see both. And then I want to look at the constellation. So let's put our constellation visualizers. Now let's run the results. This is, you have to run OptiSystem again so that it loads the data and updates the visualizers. Now, the result is not going to look quite correct. And the reason is actually I have not set the coherent receiver frequency correctly. So you can see actually the solution, the constellation, the rotation of the constellation visualizer due to the difference in frequency. Now let's put these at 1550 because that's the frequency of our laser. Let's try it again. And there we go. This is how you can use OptiSystem to visualize results from OptiSPICE. Now let's go back to our presentation. Now, this is the starting point of our OptiSystem and OptiSPICE CoSimulation. In OptiSPICE, like I said earlier, you can use transistors and build a laser driver out of transistors. And this is this laser is using the laser rate equation model and uses a current that goes into the laser for the direct modulation. I have a bit generator here that is driving this in push-pull configuration. And on this side, I have an optical fiber. And on the other side, I have a photodiode, and I have 2 subcircuits representing different amplifiers. I think it's a good idea to take a little break here, and I'm going to just hand the mic over to Brian, and he's going to be doing a second poll, and then I'll take some questions, and then we'll continue with our presentation.
Okay, thanks, Jim. We're going to go ahead and launch the second poll here and give you guys a chance to answer that, and also type down any questions that you have for Jim to answer. Please do so if you have any SPICE, and they can be even like application requests or capability questions and whatnot. It doesn't have to be a question that you want necessarily answered right now. If there are questions that would require more of a one-to-one discussion with you, we can take the question down and afterwards reply to you via email, or maybe just pop online with you one-on-one and discuss the concept that you want to try to accomplish with the tool. And again, there are going to be 2 more OptiSPICE sessions coming up. Looking at the schedule, we have one tomorrow. It's going to be at 11 a.m. Eastern Standard Time, and there's going to be a final one on Friday, also at the same time at 11 a.m. Eastern Standard Time. So if you haven't registered for those, please go ahead and do that right now. I'll go ahead and put the link in the chat window in probably about 15 minutes or so. Otherwise, you can just go to the home page, click on the Webinar Week banner, and you'll see the list of all the webinars posted there. Okay, I think that's good for the poll. I'll go ahead and pass it back to Jem to see if he wants to answer any of the questions.
Okay, so we have, let's see if we have any questions here. We have a question asking about if we can model device physics such as p-n junction for energy band gap and carrier depletion. OptiSPICE is meant to simulate compact models. If you have a compact model, that can simulate that, yes. Usually these effects are modeled using distributed simulators that are dedicated for running drift diffusion simulations to model the distributed effects. But if there's a compact model for it, yes. Right now we don't have, well, we can model the carrier depletion. For example, if you're doing the modulation of a ring resonator using carrier depletion, we can model that. But again, it's a compact model, and it does not model the distributed effects. I'll wait just a little bit more. Have another question that we can take directly later. So I'll move on with the presentation. Okay, so here we're looking at the co-simulation between OptiSPICE and OptiSystem. Here I have the layout from OptiSystem. On the left side, the first one is we generate the signal that goes into OptiSPICE, and I'm going to show you how we handle the input into OptiSPICE in a moment. We generate a random beat sequence, we can visualize it, and then later OptiSPICE takes this input and it actually drives the laser, and then the output of the laser driver is then, you can see it here, it is fed into an optical fiber. OptiSystem has many different optical fibers and many different very detailed optical amplifier models, so you can use one of those if you're interested. And then on the other side of the optical fiber, we're feeding this information, this result, back into OptiSPICE, and we're running the simulation at transistor level. If you can see over here, OptiSPICE simulations are all at a transistor level, where OptiSystem simulations are at a system level. And then you can load the results back into OptiSystem from OptiSPICE to, for example, look at the eye diagram. Now let's look at our OptiSPICE simulations. Let's close this. Okay, so the first subcircuit that, okay, actually let me start by the system first. The way you load a SPICE schematic into OptiSystem is actually using our OptiSPICE netlist component. You just need to link, find the netlist file name in OptiSPICE, and it is going to load the schematic into here. You cannot directly reach the OptiSPICE schematic from here, but you can actually open it. Over here. And you can, now you need to make sure that, of course, your transient times are the same. Here, one thing to note, I didn't have to worry about the sampling rate because we're getting the data. These are electrical inputs from OptiSystem. We're getting the data directly from OptiSystem, which then forces the engine to run at the time step that is defined for the input. So we don't have to worry about it if you're putting data in from system into SPICE. But one thing we need to worry about is actually making sure that the stop time or the transient simulation time is the same. Also, before running OptiSystem simulation, SPICE needs to be configured for CoSimulation. Now I'm going to show you the second circuit, the optical receiver. And this is the optical input, so we can do both optical and electrical inputs from OptiSPICE into OptiSystem and vice versa. So this is the optical input from OptiSystem into OptiSPICE, and we have the photodiode, and we have idealized transimpedance amplifier that we're simulating here. Now I'm going to show you how to run the simulation. Like it's already set up here. You just click Run. What's going to happen is system is going to first call, so it did generate the input, it called OptiSPICE. Now OptiSPICE is going to run. And then it's going to take the output from OptiSPICE and then run the optical fiber, and then it's going to call OptiSPICE again for the receiver. Now we ran the simulation for the transmitter. Now it's running the simulation for the receiver. Now, the data transfer between OptiSPICE and OptiSystem is done via text files. So it takes a while sometimes to load and offload the data between two. Okay, our simulation is complete. Now we can look at a few things. For example, you can look at the frequency, the time domain representation of the signal, or you can also look at the frequency domain representation of the signal. Let's put a spectrum analyzer here. There we go. This is the spectrum of the signal. Here you can see one thing to note is you are seeing the ringing of the laser as we're turning on and off. This is due to the laser rate equations. This is the output from the optical fiber. And then here, this is the output from at the end of the second amplifier. And now let's look at the eye diagram. You see, I don't have any noise in this system, so the eye diagram looks pretty clear. Obviously, Q factors doesn't even show up. It's pretty high, but that's how you can do OptiSystem and OptiSPICE co-simulations. So now I'm going to move on to talking about ring resonator simulations. There are a few different ways of doing the ring resonator simulations in OptiSPICE. We have a built-in ring resonator model, or you can build one explicitly. Here I have built one explicitly for demonstration purposes. It's basically two cross couplers and two waveguides using our famous multi-layer filter model. Here they're set up, so this represents the ring, and then the cross coupler represents the coupling from the top waveguide into the ring, and then from the bottom waveguide out of the ring, in and out of the ring. And the multi-layer filter represents, the two multi-layer filters represent two different sides of the ring. They're set up as a single layer. However, a multi-layer filter can be set up with multiple layers with different refractive indices, and it will simulate the delay, the time delay between the two layers, and then it will also simulate the reflection and the transmission coefficients correctly, and it will calculate them depending on different refractive indices. It will also apply the correct phase shift. Now this is the explicit multi-layer filter, and as you can see, we can sweep the frequency, the wavelength of that's coming out of the laser at the bottom. You can see the results, and you can see the output and the output of the drop port and the through port of the ring resonator here. It's pretty idealized. It works quite well. And let me show you actually the same setup using both the multi-layer filter, explicit and the implicit multi-layer filter. Here we have two ring resonators. The top one is set up using an implicit model. The way you set up the model, there's no difference between the implicit and the explicit multi-layer filter based on the way you set it up. You can have the ending index, the starting index, the ending index, and you can have multiple indexes in between, and then this thickness represents, you can have multiple thicknesses if you have multiple different indices and multiple layers. And you can see, I'll show you how we set up the explicit one. Again, you can see I have set up them the same way, but the main difference is this filter type. This is explicit, the other one is implicit. And I'll talk about the differences when we get to the transient. Now, this simulation actually sweeps the frequency of the laser. The way we do that is actually using a DC sweep. Here our DC source controls the voltage, so I call this V lambda, this node, controls the voltage that's coming out of this node, and this node controls the carrier frequency node. It controls the frequency output of the laser. It controls both of them, as you can see. And this simulation is actually set up as a DC simulation, so we're sweeping the voltage, and this voltage represents the wavelength of the laser. So I'm sweeping between 1450 to 1550 nanometers with 0.01 increments. Let's quickly run the simulation. For this DC simulation, the only thing pretty much that's important for the multi-layer filter is we get the correct phase shift and the correct loss, and both models actually generate the same result. Now I'm going to go and do the same simulation, but I'm going to do it in transient instead of DC. So we're not going to be sweeping the frequency, but we're actually going to be putting a impulse into this ring, into these rings, and then I'm going to be looking at the results. Now I turned off, so I'm not controlling the carrier frequency anymore. It's turned off for both lasers. But I have a voltage source that inputs a sharp Gaussian pulse into the ring resonator. Now again, let's run the simulation quickly. Okay, so you can see the impulse actually traveling. This is, let's see, the cross coupler. This is the drop port of the top ring resonator. Sorry, it's the bottom one. So this is the drop port of the bottom ring resonator. You can see the multi-layer filter. It models both the phase shift loss and the delay, the time delay of the ring resonator. However, the implicit model, it only models the phase shift. It does not model the phase delay. Therefore, all these signals, they just come out all at once. So this is the most important difference between the multi-layer filter, the explicit one, and the implicit one, where in the explicit one, we are modeling every layer separately and explicitly, where in the implicit multi-layer filter, we're actually just putting all the layers and then calculating a transmission and reflection coefficients and simulating it that way, so we can't have certain filtering effects and we can't simulate the delay. Doing it using the implicit multi-layer filter, it helps you speed up your simulation, but then you lose some of the effects you can normally simulate. Okay, so we went through this. Okay, so I'm going to now show you a more complicated ring resonator simulation. We have a ring switch here, which uses a subcircuit. The way the simulation works is we have multiple rings, you can see here, connected all together, and by turning the rings on or off resonance, you can actually control the signals that where it comes out, where the signals come out. You can have a signal coming from the north and going to the east or west. You can route the signal however you like. One problem with the ring resonators is they're not perfect filters, so they actually leak some of the signal, and this leak results in crosstalk. So as you can see here, we have the input, and then you can see the output of the same signal. There's a little bit of a delay because it goes through multiple rings, and this is done using the explicit filter. And you can also see the crosstalk and how the signal gets disrupted by interactions from different input streams. As you can see, all the input streams have different bits and different they're on the same frequency, but they have different bits going in. So I can actually, I would like to show you the subcircuit for this, because it's actually a nested subcircuit. So OptiSPICE does not have a limit on how many subcircuits you can nest within one another. So we have 4 lasers, and then each laser is directly modulated, sends a signal in, and then they all come up from a different port. Let's double-click on this to go into the subcircuit, and then actually I'm going to double-click into this to see we have more subcircuits underneath, and if I'm not wrong, this is also a subcircuit. So you have multiple levels of subcircuits to clean up the design, make it easier to visualize and manage your devices and circuits. Here we have a ideal mux Dmax. Again, this example has 2 subcircuits. One is for the mux and the other is for the Dmax. I mentioned earlier that OptiSPICE can handle multiple channels and multiple frequencies at the same time. So here we're actually taking lasers with different frequencies, and then we're muxing them all together into one. You can see they're all joined together, and then sending them through one fiber, and then on the other side we can demux it. These channel filters can be configured to allow or block certain channels. So you can configure your ideal Dmax pretty easily. I'm going to quickly run the simulation, and then I will show you how we build subcircuits. Let's run the simulation. Okay, we can look at the results. Here you can see the output of different channels. Actually, if I let's place a few probes here so that we can all see the input and the channels as well. And I am going to run this a bit more quickly. So let's say 5 nano. And now you can see all the optical input and all different channels. Okay, now I'm going to briefly show you again. If you double click on this, you can see the subcircuit. One other thing you can do with subcircuits is actually you can define parameters for them. If you right click parameters, I have defined gain or loss, if it's positive or negative, for this device, and I have used this gain in these optical gains. The way to do this is actually, if you right click, once you generate your subcircuit, you can edit. There's an XML here that will let you define different parameters for the subcircuit and then use them internally. Now let me go briefly show you how to generate a very basic subcircuit. Let's see, maybe we want to do an electro-optic subcircuit, so let's start with a basic laser maybe. And then we want to split the signal into two. Okay, so we have two optical, two electrical ports. Now, it is possible that you have already designed your circuit. What you can do is you can remove all the input. And of course, I first need to save this design. Let's save it. Subcircuit example. Now, first we need to place the input and output ports. So you can do that from Options, Subcircuit, New Port Connector. Well, for optical, we can select bidirectional. We can name it as Out1. One important point to remember is, unfortunately, our ports come automatically as electrical connections, so you won't be able to connect them directly to optical. So you have to select, change the type of the port. So in order to do that, you go to Attributes, Type, then you type Optical. Then now they connect together. Now I'm going to generate a second one. And then let's rename this. Let's call this Out2. Okay. We can also do the same thing for the electrical ports. Say in magnitude. You can rotate these devices by either right-clicking on them or rotate left, or you can use the subcircuit Control R. So a shortcut. Okay, let's place the other one. Now we have finished designing our subcircuit. Now we want to place it, for example, in our library. To do that, we can create. We go to Options, Subcircuit, create subcircuit block. Now you can select a pre-designed circuit here. So we want to use this circuit here to create a subcircuit. It also allows you to select the other ones, but I'm going to select ours. It's called Circuit 9. It automatically places your ports for you. This determines the location of the ports when it generates the icon for the subcircuit. Let's call this my subcircuit 1. Now we have different libraries. The user can generate its own. The users can generate their own libraries. Now I'm just going to create a new library for this, for a particular user, and we can call it. We can save it over here. Let's call it my library. Okay, and then it will be added. Once we created this library, we can select it, and it will be added, and this model will be added to this library. You can see initially the icon is very simple, but then you can right-click, edit part, and you can actually edit the icon and change its shape. And one final point I would like to make is you also need to, if you have optical ports, you also need to make sure that the output ports of the subcircuit is in the correct format, so in the correct type. So we need to make sure that we type optical here. Okay, now we're done with this. I'm not going to change the icon. And now we can actually drag and drop the circuit, and you can see these are electrical connections. These are optical connections. That's it for today. Now we're going to take another break and have another poll. And after the poll, I'm going to be answering some more questions. Thank you for listening.
Okay, so let's go ahead and get this last poll. And of course, everybody that's been attending the webinars, these are the same polls, and they give us really good feedback for the audience that we're presenting to. So again, your participation's greatly appreciated. We do plan to keep on doing webinars, and perhaps if this is a very successful week, which it already looks like it will be, we might be doing this a little bit more regularly. And what we're trying to get a good grasp of is to understand if our audience wants us to do more introductory level sessions, or maybe some application specifics, or maybe just feature sets of the tool. I know a lot of people have very niche applications that they might only use a couple features in the different software tools that we have. So again, any information that you guys can provide, whether it's a question specifically about our capabilities, or if you just want to write in the questions panel some suggestions of what you're looking for in this type of tool, we can definitely take those and discuss with you afterwards our development plans, and if we can fit that type of feature set into our tool. So I think with that said, there are a couple questions that came in. I'll give Jem just a little bit more time to read through them, and I'll go ahead and close the poll right now. And I think it's a good point to pass it back to Jem, and I'll let him finish up with you guys. Thanks.
Okay, here we have one question regarding if silicon photonic circuits, including source, waveguide, detector, can be simulated. Well, we can both OptiSystem and OptiSPICE can simulate silicon photonic circuits, including the source and the waveguide and detector. The way, like how I presented in this presentation, to use OptiSystem and OptiSPICE together, the best way is usually doing the electrical part in OptiSPICE and using some of the more advanced components of OptiSystem to complement OptiSPICE on the photonics side. However, OptiSPICE can also handle photonics models on its own. So there are a few ways you can work with your circuit, with your design. So I'll wait just a little bit more for other questions. In the future, so one of the questions here is asking about the files in this presentation. We are going to make them available in the future. We don't have a set time yet, but we can make both the presentations and the examples available. Yes, we can actually take into account. So there's a question here if it's asking if we can take the nonlinearity of the modulator into account. Yes, we can. For example, one of the examples you can do with the nonlinearity of the external modulator is creating a comb. You can use it to do a comb generation. So that's one way you can use the nonlinearity of OptiSPICE. The other question is if OptiSPICE can simulate PAM4. Yes, it can. It doesn't have any. You can, as long as you use our voltage-controlled source. There are a few ways you can do it. Obviously, you can either use it direct modulation or external modulation. I think that's it for today. There are a few other questions that we'll take on offline directly. Thanks for joining me at this presentation.
Thank you, everybody. Have a good day.